Hey everyone. All right, so let's take up the homework for the component method questions here. Now, as discussed in the last video, I am a pretty big proponent of the component method. I think generally speaking, the component method is the superior way to do 90% of the questions, even the ones that you could get away with using sine law and cosine law, with some notable exceptions. There are some cases where sine law, cosine law works faster, and those are the cases where one of the two vectors that you're working with plays nice. Either one of the two vectors on the north line, south line, east line, or west line, especially if it's the first vector. But with a question like this one here, where both vectors are not playing nicely, or as I like to say, play nice, in these cases, you're going to find that the component method is much, much, much more reliable. But anyway, we're going to explore these ideas. First step, let's take a look at this question. We got a plane, it flies 200 kilometers and north 60 degrees west. It then flies 600 kilometers south 30 degrees east. We need to determine the plane's resultant displacement using D as the notation. Using sine law and or cosine law for part A and for part B, the component method. Again, with this particular question, on a test situation, I would never expect you to use sine law or cosine law for this one. The component method would be better. And just to give you some sort of anecdotal advice here, I've been teaching physics for a very, very long time. And historically speaking, especially in the earlier assessments, when students have the option of using sine law, cosine law versus the component method, with using sine law, cosine law, the problem is with finding the final angles. That's where most students have the problem. And from my experience, students get it correct 30% of the time when they use sine law, cosine law, especially at the very beginning. Whereas students who choose to work with the component method, about 80% get it right. So I find the component method is just a much more reliable way of doing things. And hopefully this will demonstrate why it has its, why I value it so much. So starting off, vector A, that's our first vector. It's 200 kilometers north, 60 degrees west. Vector B, 600 kilometers south, 30 degrees east. All right, so we're looking for the magnitude and the direction of our displacement. And let's make that harpoon a little bit more harpoony. There we go. Now, as mentioned before, I like using this notation, the resultant, and then we'll use this displacement notation in the therefore statement. Because, displacement is just a type of a resultant. That's all. Step one, in the solution section, you always start with your vector equation. And that is our resultant is equal to vector A plus vector B. Next, your vector diagram. And with your vector diagram, have your wits about you. Because vector A has a magnitude of 200, but vector B has a magnitude of 600. What that implies is that vector B is 3 times longer than vector A. And that should be reflected in your diagram. Since neither of these two vectors are playing quote unquote nice, you need to start off with your compass rose. So our first vector was 200 kilometers north, 60 degrees west. Now, notice how I'm drawing this. I'm not actually measuring the angle. I'm just kind of guesstimating here. That's 45. So your 60 is actually 2/3 of the way around here, because this is a 90 and 60 is 2/3 the way. So let's say, let that be our vector A right there. And I'm just going to make sure that all right, perfect. Now, here's where things get tricky. Our vector B is 600 kilometers. So we're going to put another compass rose here. Very key. Now our next vector is 600 kilometers south, 30 degrees to the east. Now, see this? That is terrible, because the way I have it right here is B looks about the same length of A. No, it's not. It's got to be 3 times as long. So obviously when we do this, it's kind of a bit of guesswork. I suppose we could use a ruler, but come on, who does that? Okay, so now here's where things become, now you're going to see where the problem is. All right, because I'm just kind of guesstimating that 30 degrees and I'm guesstimating the length. And that has an effect on our resultant. So I'm going to make that red for resultant. Now, look where I put the head of the resultant. It has to go to the head of vector B. Okay, so the thing is, if I had sketched this a little bit shorter and I got the angle a little bit different, your resultant now all of a sudden looks like it's going a bit more west. So you really can mess up easily, especially a question like this, your directions. Because your diagram, there's a good chance that your diagram is out of scale and maybe misleading you a little bit. So that's the issue here. So when you look down here, and I'm talking specifically this right here, we don't really know if the resultant is supposed to be a little bit east of the south line, or maybe even directly south, or a little bit west of the of that south line. So we have to rely on the numbers and not rely entirely on the diagram, which I find innately offensive because having to do guesswork with the diagram, that's where I find it to be a problem. So where component method, none of that exists. It is completely rigorous, and it is absolutely insulated from the sketchiness of how you draw. All right, so I digress. Let's analyze it. Let's put some numbers in. Let's get some angles and stuff. Okay, so first of all, vector A was north, 60 degrees west. So that was that. That's 60 degrees in there. Now, also, just to save us a headache, I am not going to carry all the sig figs in the interim calculations. We'll just use the appropriate number of sig figs at the end, just because it does become onerous to carry all those extra digits. The second vector was south, 30 degrees east. Okay, so now here's the situation. And I'm actually going to color code this. The reason why, because we have to do a little bit of geometry. Oh, shoot. All right, now here's the deal. We need to get an angle inside this triangle. We need to get at least a 1. So now we know the magnitude of this side. So we know that that's 200. And this side is 600. But we don't have any angles yet. So we need to find some angles. Oh, I should also label my resultant. There we go. Resultant. So we need to find one angle. And the angle that I suggest we find is this angle R. And I'm just going to write it as a capital R. So here's the situation. To find angle R, we have to recognize a couple of things. First of all, this whole angle in here is also 60 degrees. Why, do you ask? That would be the Z pattern. That was so poorly drawn. That's not much better, but you can see that there's a Z pattern there. There, Z pattern. I will not be defeated. Anyway, all right, so now we need to figure out this angle R. Well, what we know is the following. And we'll do a little aside over here. We'll do it right here. Angle R plus 30 degrees is equal to 60 degrees. Oh, and I also need to do this. Don't forget to write the Z pat. So angle R is equal to angle R plus 30 degrees. So 30 plus R is equal to 60. So our angle R is equal to 60 minus 30, or 30 degrees. Okay, great. So now we have side, angle, side. And since we have side, angle, side, we can start off by finding our resultant, or the magnitude of our resultant. And to do that, we're going to be using good old cosine law. So we'll make our little heading, find the magnitude of R. All right, so we have vectors R, A, and B. So the magnitude of R squared is equal to the magnitude of A squared. Let's do that again, a little cleaner. The magnitude of R is equal to the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B cos of angle R. So now to get R by itself, we take the square root of both sides. And that just gives me A squared plus B squared minus 2AB cos of angle R. Substituting our values in. All right, so now here's my recommendation again, is I would actually solve for everything under the square root for later use. Now, if you have a fancy calculator, that should actually do that for you. It should actually give you a reduced value. And then given the option, not a reduced value, sorry, a non-rounded fractional value, so to speak. So that's what I'm going to do using my fancy pants calculator. Honestly, who the heck says fancy pants? Old physics teachers. Anyway. All right, so that gives you 400,000 minus 240,000 times root 3 over 2. Now, you're only in grade 11, and you don't know this yet, but there are some special angles that you can get with cos and sine of 30. So cosine of 30 actually works out to root 3 over 2. If you don't know that, that's literally totally fine. That's something you don't really usually learn until grade 12 anyway. But in any case, if you plug this into some calculators, it actually will give you this value right here. All right, so this reduces down to 400,000 minus 120,000 times root 3. And that 0 needs to be fixed there. Okay, so now, again, I know I'm being kind of ridiculous about it, but this here is actually a better number to use in a future calculation that involves the magnitude of r. That's not always practical, I understand that, but I would be remiss if I didn't give you that option. So this works out to 438.354, and just obviously we were going to round off to the appropriate number of sig figs later, but for now, we're going to use that value right there. So this is better. This is fine too. But again, there's going to be rounding error in this. So let's focus on that next, because the next thing we have to figure out is an angle. All right, so here's the deal. We think that the resultant is south and a little bit east. We may be wrong with that. So this little piece there, that is our theta r, the direction of our resultant. Maybe. That's assuming I drew this correctly. Okay, so now we have some work to do, because to figure this out, we have to figure out this whole angle inside here. I'm running out of colors here, so I'll use that hue there. So this whole thing is our angle B. So now we have our angle R. We've now got our side R. We've got our side B, and we're looking for angle B. And again, we could use sine law, but B looks like it's going to be obtuse. So I'm going to say no to sine law. In my opinion, you should be using cosine law. So again, see how here's another thing where you could mess up really, really easily. So I don't like this method, man. I'm telling you. But regardless, this was my idea. All right, so we have to find angle B, and we're going to use the cosine law or the cos law. That's very delicious on bratwurst. That's a terrible joke. I'm totally sorry. Okay, anyway, magnitude of B squared is equal to the magnitude of, A squared plus magnitude of R squared minus 2AR cos of angle B. All right, so again, this is our term of concern. So I want to isolate that, and that's good old Bedmus in reverse. So that's a little bit of a SAM-DEB action. So the first thing we have to do is the subtraction addition. So this term, I want by itself. So I'm going to bring this term to this side, and I'm going to bring that term over to this side. And we're going to be doing that through addition and subtraction. So that gives me 2AR. See, I'm dropping the vector notation now. My R's are looking pretty terrible, I'm not going to lie. Okay, so now don't forget, this becomes negative when you bring it to the other side, and this becomes positive. Cool. All right, so the subtraction addition is done. So now we're left with multiplication / division. And of course, it's these things that we need to get rid of, and they are attached through multiplication. And the opposite of multiplication, of course, is division. So cos of angle B is equal to A squared plus R squared minus B squared over 2AR. All right. So now, and then the final step is we have to get angle B by itself. And that means we have to get rid of the cos. The opposite of cos is cos inverse, or arc cos, as I often refer to it as. Okay, so now here's the deal. It's the R that's the issue. Using this value up here, the highlighted one, this one right here, is going to give us a better quality result. That is true, but that's not going to be a lot of fun to substitute in here. So if you were smart about it and didn't clear your calculator, this is probably still in the memory of your calculator. And if you store that number in memory and then use the recall function, then you have a much better chance of having a cleaner answer. So I'm not going to substitute in that more exact statement. I'm just going to put in that 438.354 and hope for the best. All right, see what we get here. I really do not like doing the question this way. Okay, so 136.81, 3 degrees. All right, so now if you're at home, again, Wolfram Alpha is kind of your friend here. So actually I'm going to do this using Wolfram as well. And because it is really helpful, especially when you're doing your homework, because it's easier to type it up on your computer than it is to use your calculator necessarily, or at least that's what I find. All right, so we're going to do the first thing where we found the resultant of r. So that was r is equal to, that was the square root of 200 squared plus 600 squared minus 2 times 200, 600, and then cos of 30 degrees, I believe. Close that bracket, close that bracket. All right, see, and it even highlights the brackets for you. It's pretty cool. And I forgot the 2 up there because I always make a stupid mistake. Try that again. Oh, right. It thinks I meant r as in the radius. For heaven's sakes. Okay. There. Okay. Now, here's the thing. See, it rounded it off, so we were right there. You also have the exact form. Hey, look at that exact form. You see that? Isn't that cool? Now, you could also go plain text, and we can actually copy this, which is kind of cool here. Yeah, so that's what we're going to do. So we copied that. Now, watch what I'm going to do. Because I have that number, so we're going to make a new tab in Wolfie. All right, so now I'm going to do this. Let r equal that thing that I just copied. And then I'm going to go comma. So now we needed to find angle B. Now, hopefully this is going to work out. And that was equal to the cos inverse, or arc cos, of, now here's the thing. I'm going to put my brackets ahead of time. So that's going to be the brackets for the numerator, and that's going to be the brackets for the denominator. Right? I didn't have to put that much space in there, but it just makes things a little easier. Okay, so now by doing it this way, I'm less likely to mess up. Okay, so I kind of forgot what the numbers were again. Oh yeah, so that was 200 squared plus our r value squared. And see, I just was able to type in r, which is kind of cool, r squared, minus 600 squared. Okay, so now tighten that up, divided by 2 times side A, which was 200, times r. And my last bracket there, clean that all up, and let's see if this works out. All right, cool. But there's one small problem. See the value B? That's in radians. So what we're going to do here is up here, I'm going to write in degrees, knock on wood, and it didn't like that. Okay, you know what? I'm just going to change the R to an X because the program is, Wolfie, you're making me look bad, man. I'm trying to sing your praises here, bud. Okay, so Wolfram still didn't like that. So I know if I add a degree symbol here, and on a Mac, it's super easy to do. It's Shift Alt number 8, and that puts in a degree symbol. I don't know how to do it on a PC. I mean, it's one of those alt codes, but any case. So if you put the degree symbol here, it eventually gives you your answer, and there we go. Now, of course, that's incorrect. So what did I do wrong? Right there. Let's try that one more time. I should probably edit this out, but I'm not going to. There we go. All right, so how close was I? Yeah, look at that, spot on. There we go. Good stuff. Okay, well, that was terrible, and I did not enjoy that, and I'm still not enjoying that. But anyway, now we got to figure out what's going on here. Okay, so here's the thing. So we now know angle B is 136.813 degrees. All right, so now we have to do some figuring here. So this little part here, we know that's 30 degrees. All right, so now the remaining part of the angle, and I'm really starting to run out of colors here. We'll do a brown. Okay, so this remainder here, and I'm going to give that a name. I'm going to call that alpha. So alpha is equal to our angle B minus 30 degrees, and that's our 136.813 minus 30, and that is 106.813 degrees. Now, we have to clarify where this alpha is being measured from. And this alpha, and I'm going to do it over here, is actually from this line all the way to the resultant. And that's what makes it tricky. Because if you didn't draw this diagram clearly, like look at how small these tolerances are. It's just ridiculous. Now, the good news is we guessed right. We guessed that this vector r is going to be beyond this 90 here, and it is. So the next thing we have to do is we have to figure out what angle r is going to be. And what we know is that this little section here is 90 degrees. So this green plus the 90 plus this value r is equal to angle B. All right, so let's do that somewhere where we have more room. Sigh. Now we need to find theta r. So theta r plus that 30 degrees plus that 90 is equal to that angle B. So that's angle B minus 120 degrees, which is 136.813 degrees minus 120 degrees. So our theta r is equal to 16.813 degrees. Yuck. Ugh, terrible. Just terrible. All right. So now let's do our concluding statement there. Therefore, we'll start off with this notation. The resultant is equal to, and round it off to 4 sig figs. So that's 438.4 kilometers, and that'll be south 16.81 degrees east. Worst, yeah, because, south and then east. All right, and of course, we need to use the right notation, the displacement notation. Okay, and then, that's what we're doing here. Okay, so I've been teaching physics a long time, and even with all these years of experience, I really don't like doing questions using this technique. But I feel that I needed to show you why it kind of sucks. And now we're going to go through the component method. So part B. And now we're going to watch how much better it is than using the other technique. It's just so much better. Okay, so here are your headings. Vector, X component, Y component. All right. So the first thing we do is we look at our vector A. Now recall, our vector A was 200 kilometers north, 60 degrees west. All right, just for the sake of convenience, I'm just throwing those numbers up here just so I don't have to keep scrolling up and down. Okay, so now we're going to start off with the vector A. So remember, it goes north, then west. So north, then west, and then the actual angle. So this is your vector A. This over here is your AY, and this over here is your AX. However, don't forget to dash your components. Now, you're probably saying, I thought we dashed the resultant. We dashed the resultant because the resultant is unknown. It's one of the things we're looking for. In this case, we actually know what the value A is. What we don't know is what these individual components are. So that's why I dashed them. It's usually the ones that we're looking for. All right, and this would be our theta A. That's 200, and that is 60 degrees. Okay, so identifying, since this is theta here, that's your opposite side. Okay, so if it's the opposite side, we know that it's going to be the sine. So AX is equal to A sine theta A, which is equal to 200 sine of 60 degrees, which actually works out to 200 times root 3 over 2. Now, again, you may not know that it's root 3 over 2. If you put in your calculator, that's going to be some ugly number like 0.866 blah, 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 blah. But I'm going to leave it like this. Okay, so it's 100 root 3 or 86.6 if you use decimal. Actually, all right, fine. I'll put the decimal too, whatever. But I'm totally using this number here later. Okay, so that's now as a vector. Oh, the struggle is real. As a vector, that is 86.6 kilometers. And look at the direction of this arrow. That's going to the west. We also know because it says west up here. See, west. Nice. Now let's do AY. No thinking involved because if we know that one is sine, the other one's got to be cos. So that's 200 cos of 60 degrees. And that works out to exactly 100 kilometers. Okay, and again, we'll worry about rounding off to the appropriate number sig figs later. Okay, and that works out to which way? Well, again, that's going north. We also know it's north up here, so north. Okay, great. A is done. Now B. So vector B, let's look at the components. South, then east. So south, then we go east. Start south, go east, and that vector right there, that was our vector B, sorry. These are our components. So that's our vector B. That's BY. That's BX. And that is theta B. This has a magnitude of 600. This here has an angle of 30 degrees. Okay, so now when we look at this diagram, BX is on the opposite side. So again, in this case, it's going to be sine. bx is equal to, no harpoon, b sine theta b. So that's 600 sine of 30 degrees. Well, sine of 30 is 0.5, so that's 300 kilometers. And which way is the x going? If you look at the arrow here, specifically that one, that's going to the east. It also said east up here, so that's east. The by is going to be cos. Because we already know that the other one was sine. Get it? B cos instead of b cut. Oh, okay. I'll just show myself out. 600 cos of 30 degrees, or 30 degrees if you don't put emphasis on the wrong syllable. So that's going to be 600 times root 3 over 2, because that's awesome. So that's something to remember. Anyway, so that's 300 root 3. Delicious. Okay, so now, again, I'm going to use that number in the future calculation, but I'll round it as well. And that's 519.62 kilometers. And as a vector, that is going south, because in our diagram, by is pointing towards the south. All right, good. So now we've found the individual components. Next step is to find our rx and our ry. Okay, so our rx is equal to ax plus bx. Okay, dropping the vector notation, our ax was equal to 100 root 3, but it's going west, which means humans of profound awesomeness, negative 100 root 3, plus bracket, bx is going to the east, so that makes that positive 300. Okay, so now to combine these, now we're going to have to deal with a little bit of rounding, but at least we've minimized the amount that we have to do. So that gives us positive 126.79 kilometers. As a vector, that's 126.79 kilometers east. And next, we take on the y component. So ry as a vector is equal to ay plus by. So ry is equal to bracket. Ay was 100 kilometers north. So north is positive, so that is positive 100 plus bracket. By was south, so that makes it negative, and that's 300 root 3. And then, now we'll do some rounding on this line, but still it's better than the other. Okay, so that's negative 419.62 kilometers. So that is 419.62 kilometers south. Now, if you take a look, we know that the general direction is going to be going south and east, which is precisely what we got in the previous question. Okay, so now that's done. Now we actually have to find the resultant. So, new vector equation, and that is vector r is equal to rx plus ry. That's followed up by the new vector diagram. So now, when you draw this, start with your x, then follow by your y. I'm very picky about that. I mean, if you want to do the y first, then the x, that's cool, but then you have to switch it in this equation here. So I want your diagram to reflect what the equation looks like. Okay, so here we go. Start off with the x component and then the y component. Now the y component is bigger than the x, so I'm going to actually shorten my x component a little bit. There we go. More like that. Okay, and then our resultant is going to be that. Okay, so now I'm going to, actually they're all part of the resultant, so I'm going to color this all red. You don't have to do that, but I think it looks cooler. Okay, and then, of course, so being internally consistent here, this is our Rx, but we know that now. This is our Ry. We know that, and this is the resultant we don't know, hence it's dashed. And this here is theta r, that is the angle of the resultant. Okay, so now to solve these, it's just Pythagorean theorem and using tangent to get the angle. So let's just do that real quick. So we're going to find the magnitude of vector r. So the magnitude of vector r is equal to the square root of the magnitude of rx squared plus the magnitude of ry squared. So r is equal to 126.79 squared plus 419.62 squared. And we got r is equal to 438.35 kilometers. Sorry, 0.352, which is what we got using the earlier method. Now, finally, our angle. And this, we don't have to do any of this, that hot mess. No, we can find it directly. So now, find theta. And we're going to use tangent. Tan theta is equal to the opposite, which is the magnitude of Ry over the magnitude of Rx. Because remember, that's where our angle is, that's the opposite side. So theta is equal to the arctan / tan inverse of Ry over Rx. Theta is equal to the arctan of 419 point number thing, 62. There we go. 126. All right. Oh, just starting to run out of real estate. Look at that. 73.187 degrees. All right, so let's round that off to 4 sig figs. So that's 73.19 degrees. Therefore, our resultant is equal to 438.4 kilometers. And that is, according to my diagram, east, then south. So east, 73.19 degrees south. And of course, therefore, the displacement is also equal to that amount. Now, let's compare that to our last answer. Let's go up here. Where are we? Okay, there we are. I'm going to copy that over there, and I'm going to bring it down here, and we're going to compare, and then you're going to notice something, and I forgot a bracket. Okay, so now, that stupid artifact. All right, there we go. Okay, so now, you might be saying, but the directions are different. No, they are not. One is measured from the east line perspective, this one, and this one was measured from the south line perspective. And those two angles are the complement to each other. 73.19 plus 16.81 equals exactly 90 degrees. So there you go. Okay, so now let's talk and let's zoom out here. Okay, so there's part A, and that is part B down here. Okay, so I got to zoom in a little bit so I can scroll. So, sorry, 1 second here, guys. So that's part B, and that is part A. So now part A took physically less space than part B did, but part A had the nightmare of trying to figure out that angle. And that problem alone is enough that should discourage you from using that method. The component method, although there is slightly more writing to be done, really requires very little thinking. It's all algorithm. You just go and you get a very robust answer consistently. So again, that's my hot take on this, is that the component method is superior. The other method is fine, but just dumb when it comes to trying to figure out those angles. So I recommend the component method. And yeah, so that's all I have to say to that. I mean, do what you like. I'm not your dad, but I will scold you if you use the other method and get it wrong. And then I will send you the URL to this rant at the end of this video, because that's the kind of person I am. Okay, folks. Well, that was a lot of fun. Until the next video.